Today, we will see the spin echo pulse sequence in details. There are many pulse sequences based on the spin echo pulse sequence. Those pulse sequences are now widely used clinically. Spin echo pulse sequence consists of two pulses, 90-degree pulse and 180-degree pulse. A 90-degree pulse entirely converts longitudinal modulation to transverse modulation. After the 90-degree pulse is turned off, the transverse modulation begins to fade due to the dephasing process caused by spin-spin interaction and external magnetic field inhomogeneity. When 180 pulse is applied to protons after the 90-degree pulse has been shut off, the direction of protons' precession is reversed and the rephasing occurs. Left figure depicts this. Once the 90-degree pulse is turned off, the spins is dephasing due to the spin-spin interaction and magnetic field inhomogeneity. Okay. And 180-degree pulse is turned on, then the direction of the spin motion is reversed, and they will meet together and make the transverse modulation. This transverse modulation is detected as signal. So an MR signal is produced immediately after the rephasing creates the transverse modulation. Okay, yeah. This moment, the time between the 180 pulse and the rephasing is the same to the time between the 90 degree and 180 degree pulses. So the time interval between 80 degree pulse and 180 degree pulse is T over 2. And the signal is detected after T over 2, and the T over 2 after the 180 degree pulse is turned off. Okay. So this behavior resembles the echo of a sound wave. As a result, the signal obtained as a result of this rephasing process is referred to as echo signal. The 90 degree and 100 degree pulse sequence is another name for the spin echo pulse sequence. This spin echo pulse sequence is a commonly utilized pulse sequence in clinical practice. Several alternative pulse sequences based on this spin echo pulse sequence have been developed and are now in clinical use. The spin echo pulse sequences are repeated several times. Yeah, 2 times. Yeah. TR stands for the time interval between two spin echo pulse sequences, equal TR, time of repetition. So this is the TR in this case, 180 milliseconds. The time interval between the 90-degree pulse and the rephasing, on the other hand, is called TE, time of echo. So this time interval is called time of echo. This TR and TE can be manipulated. So we can control these two times. We can get various weighted images by controlling these two times, TR and TE. Two spin echo pulse sequences and the accompanying echo signals are shown in the figure. So we have two spin echo pulse sequences, and the interval between two pulse sequences is TR, time of repetition, and after 90-degree pulse is turned off, we have echo signal after TE. So TE time after the 90-degree pulse is turned off, we have echo signal. As seen in the figure, the longitudinal modulation begins to revert to its previous value shortly after the 90-degree pulse of the first spin echo pulse sequence. So at this moment, the longitudinal modulation is recovering at this moment and recovering, right? And here we apply another spin echo pulse sequence. As a result, the magnitude of the longitudinal modulation right before the second spin echo pulse sequence's 90-degree pulse is recovered up to this value. So from here, longitudinal modulation is recovering, and after TR, we have this recovered longitudinal modulation. This longitudinal modulation is flipped completely to the transverse modulation by the 90-degree pulse of the second spin echo pulse sequence. So here, at this moment, this recovered longitudinal modulation is flipped to the transverse modulation at this moment by this 90-degree pulse of second spin echo pulse sequence. The transverse modulation decreases as a result of the dephasing process after 90 pulse is switched off. So transverse modulation is decreasing here right after this 90-degree pulse is shut off. The transverse modulation is decreasing due to T2 relaxation. Even if the 180 pulse is switched off at this moment, the dephasing continues. So dephasing should be continued, right? Once the 180-degree pulse is switched off, protons rephase, and an echo signal is produced at time of T after the 90-degree pulse is turned off. So the echo signal is produced T after the 90-degree pulse is shut off. Okay? So the echo time, T. Thus, the transverse modulation will be diminished by the factor of exponential minus T over T2 over this time. So transverse magnetization is decaying for a time of Te. So the decreasing factor is given by this form. So as a result, the echo signal intensity is the product of this value and this value. Okay, so we have the echo signal intensity is obtained by this expression. This signal intensity can be also seen in relaxation time curves. Left figure depicts this. The recovering longitudinal magnetization during TR is totally switched to transverse magnetization by a 90-degree spin echo pulse sequence, and thereafter this transverse magnetization decays. Okay, so in this figure, longitudinal magnetization is recovering during time of TR, and at this moment spin echo pulse is turned on, so transverse magnetization is decaying, and after TE we have echo signal, right? So the spin echo pulse sequence refaces this fading transverse magnetization, which is detected as echo signal after the duration of the E. So once more, longitudinal magnetization is recovering for the time of TR, and at this moment spin echo pulse is turned on, and the 90-degree pulse of the spin echo pulse sequence flips the longitudinal magnetization to the transverse magnetization, and this transverse magnetization is decaying due to the T2 relaxation. So T after the 90-degree pulse is turned off of the spin echo pulse sequence, we have echo signal here. Okay. As illustrated in the figure, the echo signal intensity is obtained by joining the T1 and T2 relaxation curves. Okay. So you can find echo signal intensity by joining the T1 relaxation curve and the T2 relaxation curve. It is important to note that the axes of the two curves are not identical. So the axis of T1 relaxation time curve and the T2 relaxation curve are different. Several additional 180-degree pulses can be applied to obtain the several echo signals after spin echo pulse sequence. So spin echo pulse sequence is given here, and after that we can apply several other 180-degree pulses to obtain the echo signal. But due to T2 decaying, the echo signal intensity is decreasing as a function of time. Now let's see the what kind of weighted images for image parameters. In imaging, tissue contrast is produced by utilizing tissue-dependent physical quantities. For imaging in MRI, several tissue-dependent magnetic properties are used. Those are T1, T2, and the proton density. So we can use these three physical quantities as image factors. The T-cell contrast is achieved via T1 relaxation time or proton density and the previously stated 90-degree FID and inversion recovery force sequence. We saw what the 90-degree FID and inversion recovery force were, and previously we already discussed that. And in that case, we saw that in these force sequences, we can get T1 weighted image or proton density images. In these two force sequences, we could not use the T2 relaxation time for image factors. On the other hand, the T2 relaxation time can be used for tissue contrast in the spin echo force sequence. The T1, T2, and the proton density weighted images are obtained using the spin echo force sequence. These images are generated by selecting proper TR or T times. Let's start with what occurs if we choose a long TR. So we choose long TR. For example, we have the T1 relaxation curve for white matter and CSF. And these T1 relaxation curves are connected with the T2 relaxation curve. If TR is long enough, all tissues longitudinal magnification returns to the original values. So here you can see if you use long TR time, then longitudinal magnification almost recovers to the original values. As a result, T1 relaxation time is unable to discriminate between tissues. So for long TR, there are two possible TE cases, long TE and short TE. So we already had a signal intensity form like this in the spin echo force sequence. For long TR, this term will be vanished. Right? So leftover form is given by this. So for long TR, the signal intensity is proportional to M0 exponential minus T over T2. So in short TE, here we can put T0, right? Short, because it's short, so we can put T0. Then this term will become 1. Okay. So for long TR and short TE, this term also becomes 1. So we have the signal intensity M0, just M0. Okay. As a result, T2 relation time does not distinguish between tissues for short TE. Consequently, we can only distinguish tissues with long TR and short T by their differing proton density, which is contained in the quantity M0. Okay? Thus, we can obtain proton density weighted image in this case. So, for long TR and short T, we have the proton density weighted image. Now let's look at the example of long TR and the long T. So here, right? Long TR and long T. The intensity of echo signal in this example is mostly determined by the expression exponential minus T over T2. Okay? So long TR, long T, the signal intensity is expressed by this form. As a result, T2 reaction time of tissues can be used to distinguish them. So, for long TR and long T, we can have the T2 weighted image. So T2 weighted image can be obtained in this case. So in summary, for long TR and short T, we have proton density weighted image. On the other hand, long TR and long T, we can have the T2 weighted image. In the case of a short TR, the longitudinal modulation does not entirely recover, and the recovery varies depending on the tissue. So for short TR, longitudinal modulation is in the progress of recovering. So not completely recovered, right? So in the progress of recovery. Therefore, longitudinal modulation of tissues are different. So we can see the difference here for short TR. As a result, T1 relaxation time is used to differentiate between tissues. Okay. For short TR, we have also two possible T cases, long TE and short TE. For short TE, this vector, we can put T0, then this vector will be 1. So short TR and short TE, this vector will become 1. So we have signal intensity in this form. As a result, T2 does not distinguish between tissues, because for short T, this term will become 1. As a result, we can get a T1 weighted image for short TR and short TE. For short TR and short TE, we can get T1 weighted image. Now let's the case of short TR and the long TE. The echo signal is too weak for this case. So short TR and the long TE. Because TR is very short, the recovered longitudinal modulation is small. So for short TR, the magnitude of the longitudinal modulation recovered is very small, so negligible. Furthermore, we have to wait for a long time for echo signal. So long t, the signal is small here, and we have to wait for echo signal a long time. So the transverse magnetic decays too much. As a result, with a short TR and long T, the overall signal intensity is very small. So in this case, it's not practical. In summary, a short TR and short T case, we have T1 weighted image. On the other hand, for short TR and long T, the signal intensity is very small, so it's hard to get the correct the image, so it's not practical. This table summarized what we discussed so far. Echo signal intensity is given by this form. Okay. And the long TR case, this term, we have to use very long TR, so we have to wait long, so this will be 0, so we have the signal intensity form like this for long TR. And for short TR, we have to use entire expression. Okay. And long TR, long T, we have this form. So signal is dependent on T2. So we have T2 weighted image. Since the liquids have longer T2 relaxation times than solids, so more transverse margination remains in liquid than in solids. There are more transverse margination in liquids, so this transverse margination gives the signal, echo signal. So as a result, the signal is greater in liquid than in solid. So, in the T2 weighted image, the liquid is consequently much brighter. Once more, liquid has longer T2 relaxation time than solids. That means more transverse magnetization remains in liquid than in solid. So transverse magnetization gives the signal, echo signal. So liquid gives more echo signal. Consequently, in the T2 weighted image, the liquid part is brighter than that in solid. So we can get this kind of picture by this equation. Next, long TR and short T, we have signal intensity just given by M0, the proton density. So we have, in this case, proton density weighted image. More protons are found in liquid. In the proton density weighted image, the liquid part is thus brighter. Okay. For short TR and long T, we already discussed that, and we have too small signal in this case, so it's not practical. And short TR and short T, we have signal intensity form like this, and this signal intensity depends on only T1. So we have, in this case, T1 weighted imaging. The longitudinal magnetization recovers less in liquid than in solid due to the longer T1 relaxation time in liquid. So longitudinal time magnetization, T1 relaxation time in liquid is longer than that in solid. Okay, that means that longitudinal magnetization recovers slowly. So the T1 the longitudinal magnetization in liquid is smaller than that in solid. So we have a smaller signal from liquid. So as a result, the signal in liquid is less than that in solid. So we have in the T1 weighted image, the liquid is darker. So we can these kinds of characteristics according to what times, what TR and T times are used. In the MR images, we can check this. Let's first see the long TR and long T, short TR and long T. TR is increasing in this direction, and the TE is increasing in this direction. So this corner corresponds to short TR and long T. So in this case, we have very small signal. So we cannot get the proper image. But in this corner, short TR and the short T, short TR and the short T. Okay. So we can have the T1 weighted image. In the T1 weighted image, liquid part is relatively darker. We can check the CSF part is darker than the other parts, gray matter and white matter. Now let's see the long TR and short T. We have photon density weighted image. In this photon density weighted image, the liquid part become brighter than the liquid in the T1 weighted image. So we can check this, right? The CSF part here, the CS part over here. So liquid is a little brighter than liquid in the T1 weighted image. The last one, TR, long TR and long T. In this case, we have T2 weighted image. In the T2 weighted image, liquid part is relatively brighter. Okay, so bright, right? So we can check these kinds of characteristics which we already discussed before. We can also see the same characteristics here. CSF is liquid, and it has longer T1 times, so CSF part is relatively dark in the T1 weighted image. Okay, T1 weighted image CSF part is darker. But CSF, a longer T2 time is relatively brighter in the T2 weighted image. So you can see here. The CSF region appears brighter in the proton density weighted image here than it does in the T1 weighted image. Compare these two images, the CSS part in this region and in this region. So CSF part region appears brighter in proton density weighted image than it does in the T1 weighted image. So you can see this kind of characteristics. Also you can see here the same property. And now let's see some example regarding the spinal corporal sequence. First example, tissue A has T1 and T2 relaxation times of 1000 millisecond and 300 millisecond respectively. Tissue B, on the other hand, has T1 and T2 relaxation times of 500 millisecond and 150 millisecond respectively. The proton density of tissue B is 0.6 times larger than that of tissue A. What is the ratio of the signal intensity SA of SB if the spinal corporal sequences TR and TE values are 2000 millisecond and 500 millisecond respectively? What is this ratio for TR 200 millisecond and T 50 millisecond? So you can compare these two cases. The signal intensity has the form, this form. So we can easily calculate just putting the numbers, right? So for 2000 millisecond TR and the T is 500 millisecond, we have the ratio of the signal intensity as given by this 7.77. And for TR 200 millisecond and TE 50 millisecond, we have the signal intensity is just 1.08. This is much larger than that, right? So that means that the image contraster is better in this case, because A tissue and B tissue are clearly discriminated by the signal. So we have a better contrasted image if you use these parameters. Okay. Next example. The brain's white matter has T1 and the T2 relaxation times of 500 millisecond and 700 millisecond. The T1 and T2 relaxation times of CSF, however, are 2000 and 500 millisecond and 210 millisecond respectively. The white matter and the CSF proton densities are the same. Actually slightly different, but we assume that proton density of these two tissues are the same. Answer the following questions on the spinal corporal sequence. First question, A. Determine the ratio of the white matter to CSF signal intensities for a TR of 2500 millisecond. Okay. we have T1 relaxation curve for white matter and the CSF. Their T1 relaxation time for white matter is 500 milliseconds, and CSF 2500 milliseconds. So T1 relaxation time of CSF is much longer than that of the white matter. So it takes more time for the proton density in CSF recover to their longitudinal organization. Okay. So the question was for TR 2500 millisecond, the signal intensity ratio, right? So you can see here signal intensity for white matter is much larger than that of CSF. The expression is given by this form. The signal intensity is given by this form. So we just put the number and we can get the signal intensity ratio as 0.64. So white matter has a larger signal intensity than CSF does, because the T1 relaxation time of CSF is longer than that of white matter, so it takes more time for the longitudinal manifestation to recover. So CSF has a smaller longitudinal manifestation. Next question B. Determine the echo time TE at which the white matter and the CSF signals are equal strength. Once the longitudinal manifestation is recovered up to time of TR, and then here spinal cord pulse sequence starts. Okay, and the transverse manifestation, which was created by the 90-degree pulse of the spinal cord pulse sequence, is now decaying. We know that T2 relaxation time of CSF is much longer than that of the white matter, so we can see the curve is slowly decaying for CSF, and comparing that of the CSF, the transverse manifestation of the white matter is decreasing much faster. Okay. So the question is intensity. So determine the echo time T at which white matter and CSF signals are the same at this moment. And we have signal intensity expression. This expression. So the signal intensity are the same, so we can put equal and put the numbers here. Then we can get the T 47 millisecond. So at the 47 millisecond, two signals, echo signals, become the same intensity. Okay. So when T equal 47 millisecond, the white matter and the CSF signal intensities are equal. Next question C. Determine the ratio of the white matter to CSF signal intensities for T equal 35 millisecond. Find the ratio of signal intensities for t equal 140 milliseconds as well. Explain two results. At t equal 35 milliseconds, we can get the signal intensity ratio 0.89. So here 35 milliseconds, the signal intensity ratio is 0.89. For t equal 140 milliseconds, we can get the signal intensity ratio is 2.41. So this is much larger than that, right? So that means that at this time we can have more contrasted image because the signal intensity are quite different here than here. At t 35 milliseconds, the white matter signal intensity is greater, and t equal 47 milliseconds, the signal intensity of the two tissues are equal. Okay, equal. And here, signal intensity of white matter is larger than that of CSF at this point. Following that, the CSF signal strength surpasses that of the white matter. After this time, 47 milliseconds, the signal intensity of CSF become larger than that of the white matter. Here, signal intensity of white matter is larger than that of CSF, but at this point, after this point, there is reversed, right? The signal intensity of CSF is larger than that of the white matter. So both signal intensities decreases as T increases. Okay? T increases, signal intensity of white matter and the CSF both intensities are decreasing. But ratio of the signal intensities rises instead. The ratio of signal intensity here is 0.89, but signal intensity ratio here 140 milliseconds, we have 2.41. So signal intensity ratio here is much larger than here. This means that we have more contrasted images here compared to here at this moment. Okay? As a result, in the T2 weighted image, the image contrast is improving. Both signals are decreasing. Intensity is decreased, but the signal intensity ratio was increased. Therefore, we can have more contrasted image at this moment. Okay? Next question. Do the same procedures for TR equal 3 2,500 milliseconds. Previously, we used TR is 2,500 milliseconds, but in this case, we used the more longer TR. Okay, so here, TR from here to here is TR, right? So we use the more longer TR in this case. The same procedure, A to C. We can just calculate the numbers because we already have the all required the numbers. So just put those numbers into the equation. You can get the for A case the intensity ratio of 0.64. So it's white matter intensity and CSV intensity. So the shear intensity, the longitudinalization for white matter is larger than that of CSF at TR equal 300, 500 milliseconds here. And B, question B, was determine the echo time T at which white matter and the CSF signals are of equal strength. So you can obtain, in this case, 30 milliseconds here. So both signal intensities of white matter and CSF are the same at T equals 30 milliseconds. And question C, determine the ratio of the white matter to CSF signal intensities at for 35 milliseconds. This moment. So you can get the signal intensity ratio of 1.05 at this time. And this time 140 milliseconds. The signal ratio is found to be 2.85. So the signal intensity ratio at this moment is much larger than that in this case at this moment. At 30 milliseconds, the signal intensities of both signals equalize. Yeah. The signal intensities decreases as T rises, as decreasing. But the image contrast improves in the T2 weighted image because the ratio of the signal intensity rises. The signal intensity was increased, right? Because here the signal intensity ratio is 1.05, but at this moment signal intensity was increased 2.85. So this number means that we have more contrasted images at this moment compared to that at this moment. Next example. The T2 relaxation times of the adjacent figures are 50 milliseconds and 100 milliseconds respectively. Determine the echo time TE at which the image contrast is the highest. The echo spin echo signal is proportional to e to the minus t over t2. We already saw that. The signal difference between two tissues is therefore proportional to the difference between these two terms. Okay. So we can get the echo time T at which the maximum image contrast is achieved by differentiating the above signal difference with T and setting it to 0. Okay. So signal intensity between signal difference between two tissues are given by this form, this expression. So we want to find the echo time TE at which image contrast is highest. So we can get the maximum point. We can get maximum point by differentiating the equation and setting it to 0. Then we can get the echo time T at which the image contrast is highest. So differentiate this expression according to time TE and setting it to 0, we can get this number. So we can choose echo time 69.31 millisecond. We can get the image of highest contrast.